Welcome to The Explainer. Today, we're diving into a really fascinating paper that suggests there's a crack in the very foundation of one of quantum mechanics' most famous models. And it proposes a radical new way to look at the particles that, make up our entire universe.
The paper kicks off with this quote, and it really sets the stage. In our everyday lives, we follow rules to keep things from falling apart. But here's the thing about science. Sometimes the biggest, most profound discoveries happen when we find a place where the rules themselves seem to break down.
So let's get into it. We're going to start with a model of the atom that I'm sure many of you learned back in school. A picture that, according to this paper, has a fascinating flaw hiding in plain sight. You probably remember this one, right? The Bohr model from 1913. Now, this was a huge leap forward. See, with the older models, an orbiting electron should just radiate all its energy away and, poof, spiral into the nucleus almost instantly. Game over for atoms. Bohr's idea was that electrons hang out in these stable, stationary orbits where they don't radiate energy, which finally explained why atoms don't just collapse on themselves. Okay, but here's where the problem creeps in. There's this fundamental rule in quantum mechanics called the principle of coherence, and it basically says that for any two particles to interact, to exchange any kind of force or energy, they have to be coherent. Think of it like two musicians trying to play a chord. If they're not in sync, if they're not coherent, all you get is noise, not harmony. Well, in the quantum world, if particles aren't in sync, they just can't interact, period. And this is the crack in the foundation the author points to. In the Bohr model, the proton and the electron are not coherent with each other. They're not in sync. So according to the rulebook of quantum mechanics, they shouldn't be able to interact at all. Which begs the question, how is this possible? I mean, we know hydrogen atoms exist. They're everywhere. So what's going on? To solve this puzzle, the paper proposes something pretty wild. It suggests we don't change the rule. We change what we think a particle even is. And this is where it gets really, really cool. So instead of thinking about an electron as just a tiny single point, imagine it's actually a little system. A system made of two internal quantum states, a spin up and a spin down, that are perfectly in sync with each other. It's a particle with a kind of hidden internal complexity. And what's good for the goose is good for the gander, right? The author applies this exact same idea to the proton. It's not just a single thing either, but a system of two coherent internal spin states. So now we have these two particles, and each one has its own internal coherent structure. Okay, you might be thinking, this is a neat idea, but does the math work out? Well, the author uses a standard tool from the quantum mechanics toolbox to see what happens. And what pops out of the math is fascinating. It predicts that this new type of particle, both the electron and the proton, can exist in one of two different energy states, which the paper just calls E1 and E2. All right, so we've got these newfangled particles with internal parts. How does that fix our original problem of them not being able to interact? Well, this is the real aha moment. A totally new way of thinking about what makes things stick together. Okay, get this. Even though the proton and the electron as a whole can't talk to each other, it turns out their internal parts can. A spin state from the proton can pair up with a spin state from the electron. And these new combinations, these new exchange points, let's call them B1 and B2, they are coherent. They're totally in sync. And this sets up a kind of quantum hot potato. Imagine point B1 is buzzing with high energy, which makes it unstable. So it chucks that energy over to B2. But now, guess what? B2 is unstable, so it immediately throws the energy right back. And this isn't a one-off thing. This is happening constantly, back and forth, in a continuous loop. And here is the punchline. The paper proposes that the attractive force we see isn't some mysterious property we call charge. No. It is this physical process. It's this nonstop, super fast game of energy tag between these coherent points. And just like that, the problem of how they interact is solved. But wait, there's more. Because this model doesn't just stop at solving the attraction problem, it goes even deeper and offers a potential explanation for another huge quantum mystery, spin itself. So if we take this idea a step further, when you map out all the possible ways the internal parts of the proton and electron can pair up, you don't just get 2 points for this energy exchange. You actually get 4 of them. Now, with 4 points in the game, the energy has a choice to make. The high-energy points need to offload their energy, and the whole system wants to find a stable configuration. And it turns out there are 2 ways it can do that. The energy can either flow around in a clockwise pattern, or it can flow in a counterclockwise pattern. And this is the big idea. According to this model, spin isn't some property that a particle is just born with. It's something that emerges from the dynamics of the system. The direction of that constant energy flow, that's what we observe and measure as a particle's spin, either up or down.
Okay, so if you thought that was wild, you might want to buckle up, because now we're getting into the really mind-bending implications, where we have to start rethinking space and fundamental forces themselves. The paper describes this incredible cascade effect. It's like dropping a pebble in a pond. That first energy exchange creates a ripple, a second, weaker exchange, and that creates a third. But here's the crazy part. The math shows that instead of spreading out, all these ripples actually collapse. They converge on one single infinitesimally small point. And at that one point, that single point of resonance where the entire interaction is actually taking place, space and time, as we know them, effectively become zero. They just cease to have meaning. So let's just step back for a second and look at what this all means, because it is pretty radical. First, it suggests that forces don't act smoothly through space, but only at these very specific, discrete points. And it gets rid of the need for the Coulomb force, for charge altogether. Instead, it proposes that charge, just like spin, might not be a fundamental property at all, but just an effect that emerges from this much deeper mechanism of quantum state exchange. And that leaves us with one final massive question to chew on. What if the universe isn't held together by some mysterious property like charge? What if it's all just the result of a constant, invisible ballet, an endless exchange of energy between hidden quantum states buried deep inside every single particle? It's a view that completely reframes the very forces that bind us and everything we see together.